This is day 1 of Chapter 5. Chapter 5 is one of our 2 chapters that focuses primarily on probability skills. Some of the material that we're going to cover today, we already spoke about and addressed in one of the lessons that involved the prerequisite skills. As we talked about at that point, although probability is not formally introduced until Chapter 5 in the book, there's some basic probability ideas that you have to have prior to hitting Chapter 5. Meaning there are things you need to know in order to do Chapters 1 through 4. So there is a little bit of overlap between the stuff we addressed earlier in the year, but it's still stuff worthy of talking about again. And there's also a decent amount of stuff in here we have not yet addressed. So, starting with the first slide here, chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. The law of large numbers says that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. So, what they're given here is an example of flipping a coin. We know that if the coin is fair, there's a 50-50 chance of coming up heads and tails, which tells us we would expect about half of the observations to be heads, half the observations to be tails. Now, if you flip the coin 10 times, are you going to get exactly 5 heads, 5 tails? Well, maybe, maybe not. But if you flipped it 100 times, 1,000 times, 1,000,000 times, the more and more times you flipped it, the closer and closer and closer we get to that 50-50 split. So that's what these 2 diagrams or graphs here are showing. That with a small number of tosses, you are going to be kind of close, but not super close to the 0.5. But as soon as you hit many, many tosses, in this case going up to 500, you're coming closer and closer and closer to that 0.5 value. Okay, general reminder, the probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. So 0 would be impossible to happen. 1 would be guaranteed to happen. Most things are somewhere in the middle, as opposed to not being exactly 0 or exactly 1. In this case, the chance of flipping a coin and getting heads or tails, 50 for each. I did 50%. Excuse me. Okay, a couple myths. The idea of probability seems straightforward. However, there are several myths of chance behavior we must address. First one, the myth of short-run regularity. The idea of probability is that randomness is predictable in the long run. Our intuition tells us random behavior should also be predictable in the short run. However, probability does not allow us to make short-run predictions. So, going back to that coin example, if you are talking about flipping a coin 1,000 times, it's pretty close to a 50-50 split between heads and tails. Whereas if you're going to flip it like 4 times, whether or not it's exactly 2-2, not so predictable. Next, the myth of law of averages. Probability tells us random behavior evens out in the long run. Future outcomes are not affected by past behavior. That is, past outcomes do not influence the likelihood of individual outcomes occurring in the future. So back to the coin flipping example, if you flip a coin and you get 5 heads in a row, it doesn't mean that the probability of getting tails on the next flip is any more than the 50-50 split. It's what happened in the past has no impact on the next flip of the coin. All right, some basic probability rules. The probability of any event is a number between 0 and 1. Just discussed that. All possible outcomes together must have probabilities whose sum is exactly 1. That's important to know in some shortcuts in figuring out probability questions. If all outcomes in a sample space are equally likely, the probability that event A occurs can be found by using the formula. The number of outcomes corresponding to event A divided by the total number of outcomes in the sample space. In other words, how many ways can what you're talking about or interested in occur divided by how many total ways could the experiment take place. The probability that an event does not occur is 1 minus the probability of the event it does occur. Okay, that connects back to that second one up here. Sometimes it's quicker to figure out the probability of something not happening and subtracting from 1 than directly figuring out the probability of that thing happening. If two events have no outcome in common, the probability that one or the other occurs is the sum of their individual probabilities. Okay, we're going to talk about that in a couple slides. And two events, A and B, are mutually exclusive if they have no outcomes in common, so they can never occur together. That is, the probability of A and B is 0. So if the two things can't happen at the same time, they're known as mutually exclusive or disjoint, and anything that can happen, the probability is 0. All right, basic example. Randomly select a student who took the 2013 AP Statistics exam and record the student's score. Here's the probability model. So when you take an AP exam, your scores are 1 through 5. You can't get decimals or fractions. Those are the only possible outcomes, 1, 2, 3, 4, or 5. And this is the individual probability of getting each one of those scores. Part A, show that this is a legitimate probability model. Okay, in order to show it's a legitimate probability model, we have to have all of the probabilities be between 0 and 1, and they have to sum to 1. So as shown in the table, all the probabilities are between 0 and 1, and the sum of the probabilities, if you add them all up, is equal to 1. This is a legitimate probability model. With this adding up individual probabilities, most of the time in real-world data, these guys are rounded off numbers. They're not exactly 0.235. It rounded off from something with more decimal places than 0.235. So it's possible here you get like 0.999 or 0.00 or 1.001. If that's the case, when you add them up, then you would just make an additional little notation here that this minor discrepancy is probably due to rounding errors. All right, with these types of probability problems, endpoints matter. And what I mean by that, find the probability the chosen student score is 3 or better. Find the probability the chosen student, find the probability the chosen student's score should be, or is better than a 3. It's definitely missing a little piece there, but you get the idea. So here, it's 3 or better. So it's a sum of the probabilities of 3, 4, 5. Here, it's just better than 3, which would be 4, 5. So you have to pay attention to the detail of these guys to see if the endpoint in the question matters or not. Okay, fleshing that out, this problem is an example of a discrete probability distribution. Endpoints matter. The probability of 3 or better is different than better than 3. Putting it in algebraic terms, greater than or equal to 3 is not equal to greater than 3. Now this is in contrast to modeling a continuous distribution with a density curve like we did in Chapter 2. In Chapter 2, whether it was greater than or equal to 3 or greater than 3, the answer was the same. So this is going to be a distinction that you're going to have to be careful with when we move forward. If it's a discrete probability distribution, like this problem, endpoints matter. Chapter 2, when you're dealing with density curves, it does not matter, and refer back to those notes if you need to. All right. Mutually exclusive events in the Venn diagram form means there is no overlap. They can't happen together. If you want to find the probability of A or B occurs, it's just the sum of their individual probabilities. If the events could occur at the same time, there is an overlap. There is something in the A and B. They're not mutually exclusive. So what happens here, the rule is you have to add the sum of find the sum of the probability of A plus the B, and then subtract off what gets counted twice. Okay, dice rolling is a classic scenario for basic introductory probability. So what we have here, 2 fair 6-sided dice are rolled and their numbers are summed. Each die has faces numbered 1 through 6. The table shows all possible outcomes for this problem. So if there's 6 ways for the first one to land, 6 ways for the second one to land, fundamental counting principle says 6 times 6 are 36 possible outcomes. So for example, this 9 right here represents one die getting a 3, the other die getting a 6, adding them together to get a 9. The smallest sum possible is 2, biggest sum possible is 12. Not all sums are equally likely to occur. There's only a 1 out of 36 chance of rolling a 2, for example. There's a 2 out of 36 chance of rolling a sum of 3. All right, on to some examples. What's the probability that your sum is less than 4? So of the 36 boxes here, 3 of them represent sums less than 4. 3 out of 36. The sum is greater than 11. Oops, I'm sorry, less than 11. Okay, less than 11 would be everything above this line I don't want to mark up with here, everything above these 3 boxes. So if we know that there's a 3 out of 36 chance of these string things happening, then there's a 33 out of 36 chance of them not happening. So that uses that 1 minus rule. It's quicker to count the 3 things that aren't making it true than the 33 things that do. Okay, the sum is a multiple of 2. What I'm going to do is circle all the multiples of 2 in red. Count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 of the 36 numbers in that table represent sums that are multiples of 2. I'm going to do the multiples of 3 in green. 3, 6, or 3, 3, 6s, the 9s, and the 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of the 36 numbers are multiples of 3. Now what we're going to do is blend them together. What's the probability that the sum is a multiple of 2 and it's a multiple of 3? So how many got both circles? 1, 2, 3, 4, 5, 6. 6 out of 36 chance that the sum is a multiple of 2 and a multiple of 3. A multiple of 2 or multiple of 3, what we could do is just count up what got a red circle, a green circle, or both. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And I think, did I count that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 24, yes. Now, we have a pretty small sample space. They gave us a table with everything in it, so there really isn't a need for a fancy formula. But we're going to do problems where counting circles isn't going to be an option. So if that's the case, we can refer back to this formula right here. In order to find the OR, when there's the possibility of both events happening at the same time, what we can do is take the probability of getting a multiple of 2, add it to the probability of getting a multiple of 3, 18 plus 12 is 30, and subtract off what got counted twice. 30 minus 6 is 24. That gets us to the 24 out of 36. Now, in general, you can answer probability questions as fractions, decimals, or percents. If there are specific instructions of how to answer the question, follow those specific instructions. I'm just going to go with a basic unsimplified fraction in the interest of time. It's the quickest, easiest answer to get. If you need to reduce it, reduce it. If you need a percent or a decimal, then divide it out. But for what we're trying to accomplish right here, right now, that fractional answer is good enough. All right, next thing we're going to look at. Going back and forth and being able to read between two-way tables and Venn diagrams. So here, our events of interest are G, your high school graduate, H, your homeowner. So we have a survey of 500 total people. They're being classified whether they graduated high school or not, whether they own a home or not. We're going to take this table and put it into a Venn diagram form. So the total number of people inside the H circle has to add up to 340. Okay. The total number of people inside the G circle has to add up to 310. We need to start with how many are shared in common here. So this in here represents the people that are both a high school graduate and own a home. So high school graduate and own a home, there's the 221 right there. Okay, then this represents the people that own a home but didn't graduate high school. There's the 119. This represents the people that graduated high school but don't own a home. That's right there. And then you're neither a high school graduate nor do you own a home. That would be the 71 right there. All right, introducing some notation that you may not be familiar with. This upside down U stands for intersection or the overlap. So this G intersect H is how we would read that, would be you're a graduate and you own a home. We could get that information from here or from here if we have both. This little C up here stands for complement, which means the not the thing here. So, for example, graduate and doesn't own a home that's the graduate, and or intersect. H would be owning a home. The H with that little exponent in the C means not or doesn't own a home. So this one means you're a homeowner and you're not a high school graduate. This means that you're neither a high school graduate nor you own a home. All right. Next problem here. It says, according to the National Center for Health Statistics, in December 2012, 60% of all U.S. households had a traditional landline telephone. 89% of households had cell phones. 51% had both. Suppose we randomly selected a household in December 2012. They make a two-way table that displays the sample space of this chance process. So one way we're being classified is you have a landline or you don't have a landline. You have a cell or you don't have a cell. Now, a little contrast here. In this previous example, we knew actual counts to fill in the table, which sometimes you do, sometimes you don't. In this case, we just have percentages or proportions. So when we fill this in, we're putting in proportions, not actual numbers. So according to the National Center for Health Statistics, in December 2012, 60% of all U.S. households had a traditional landline. So the landline, the total, is 0.6 for the 60%. 89% had cell phones. So the total going across for cell is 0.89. 51% had both. So that means you have a landline and you have a cell. Well, if this column has to add up to 0.6, and that's 0.51, that's 0.09. This way, these two numbers have to add up to 0.89. That makes this 0.38. Right. All four of these represent everything. So add those three up and subtract from 100%, and you get 2% or 0.02. Add this column to get 0.40. Add going across to get to 0.11. And whether you add across or down, that gives us the 1. All right, so make a two-way table that displays the sample space for this chance process. So that would be the two-way table. Okay, second thing is construct a Venn diagram. So the two things of interest here are cell phone, landline. Okay, this here would represent people that have both a cell phone and a landline. Well, cell phone and a landline is 0.51. And again, we can do the Venn diagram with actual counts or percentages. This is cell phone, but no landline. That's 0.38. This is landline, but no cell phone, 0.09. This is neither landline or cell phone, 0.11. And we can check this. If you add up all four of those numbers, rather, they should add up to 1, and we do. Okay, find a probability that the household has at least one of the two types of cell phones. At least one of the two types means everything but that. It means everybody but people that don't have either. So that would be 0.89. Find a probability the household has a cell phone only. That's 0.38. Something's not right with that 0.89. I think I made a mistake here. I copied the wrong number. This is the neither over here is the 0.02. I'm sorry. This is 0.02. Oop. So that's 0.98. All right, let me go back and fix that. I apologize for that error. This represents you have neither a cell phone nor a landline. When I looked at the table, I looked at the wrong number. I'm not sure if I pointed to the correct one or not. I'm sorry for that error. This is 2% are the people that have no landline, no cell phone. If you add that up, that's what adds to 1. If we added that original up, we would have found that mistake a little quicker. So to answer question C, find a probability that the household has at least one of the two types of phones. That's everything but that 2% that have neither. Okay, another example. Debbie and Matt are waiting to hear if they will get partner in a law firm. Debbie estimates her probability of making partner is 0.7. So putting that into probability notation, P of D is 0.7. Matt's probability of making partner is 0.5. P of M is 0.5. Find the probability that they both make partner is 0.3. So the probability of D and M is 0.3. Part A, make a two-way table that displays the sample space of this chance process. B, construct a Venn diagram to represent the outcomes of this chance process, and then answer the following. All right, in the interest of time, I already started this. Let's see if we can see that. That looks good. All right, so the two-way table. This represents Debbie makes partner, yes, no. Matt makes partner, yes, no. So it told us that the probability that they both make partner is 0.3. So that goes in the yes, yes spot. And the probability that Debbie makes partner is 0.7. So the Debbie yes is 0.7 for the total. That means that's 0.4. Probability that Matt makes partner is 0.5. So Matt, yes, that's going to be 0.5. That makes this 0.2. So that's 4, 7, 9. That makes this 0.1. That makes that 0.5. That makes that 0.3. That makes the total 1. Okay, getting that information into a Venn diagram, this would be the and. So that would be the 0.3. This is Debbie makes it, but Matt does not. So Debbie makes it, Matt does not. That's 0.4. Matt makes it, Debbie does not. So Matt yes, Debbie no. That's 0.2. Neither of them make it. That's the 0.1. If you get that from there, add those up and subtract from 1. Okay, interpret and answer the following. So in probability notation, P, D, or M would be Debbie, Matt, or both make partner. Remember, or in the probability sense doesn't mean mutually exclusive. It means that it could be both. It's one, the other, or both. All right, so that is a probability of 0.9. The probability that Matt does not make partner is the DC. The little c up there means that not occurring. That's a 0.3. D and MC, or M complement, is actually what that C stands for. I'm not sure if I said that or not. So that means Debbie makes partner Matt does not. That's 0.4. And DC, MC means she doesn't make partner and they don't make partner. And she doesn't make partner, he doesn't make partner. In other words, neither of them make partner. That's the 0.1. All right, last thing we're going to be looking at for today. Venn diagrams aren't limited to just two circles. In theory, there could be an infinite number of circles. We're not going to go beyond 3. The 2 are the most common, 3 is the most you'll see. So for this example right here, it says common sources of, caffeine are coffee, tea, and cola drinks. Suppose that of all adults, 55% drink coffee, 25% drink tea, 45% drink cola, blah, 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 all the different categories. Draw a Venn diagram to illustrate this situation. What percent drink only cola? What percent drink none of these beverages? All right, so I'm going to draw 3 overlapping circles. I'm going to do such like this. We're interested in coffee, tea, and cola. The number that we want to begin with is always going to be that and, all 3. If we know that number, that's where we want to start. So that 5%, drink all 3. Then from there, we're going to work our way out. This football shape right here that I'm tracing, that represents people that drink coffee and tea. So the coffee and tea is 15% in that football right there. Well, if that's 5, that has to be 10. Then I'm going to go this way. In this oval shape right here, that represents cola and coffee. Cola and coffee is 25%. If there's already 5% there, that leaves 20. Same story here. That's tea and cola. Tea and cola. Did they give us that one? Okay, we don't have that one. We'll have to go back to that at a later time. Okay, let's go to this one right here. Okay, that's the coffee. Okay, 55% drink coffee. So 55% drink coffee, that means all of these numbers have to add up to 55%. So 20, 25, 35, that leaves 20% here. And I've kind of lost track of where we are. Okay, that one we've done. The 5% drink all 3, we've used that. The 15%, we've used that. We've used that. So let's go to this one next. 5% drink only tea. So 5% drink only tea. That's the tea circle that's not included in the other 2 circles. That goes there. Now we can go to the whole tea circle. Is 10, 5, and 5. That's 20. And according to this, 25% drink tea. So that leaves 5% right there. Let's just double check that. 5, 10, 15, 25. There's a 25% drink tea. Okay, 45% drink cola. That means that's that whole big circle there. 20, 25, 30. That leaves 15% for this because 45% drink cola. Lastly, we have the neither category. So we got 20, 30, 35, 40, 45, 65, 80% in there. So that leaves 20% that don't drink any of those 3. So let's go back and see what they're asking us for. Draw a Venn diagram and illustrate the situation. Done. What percent drink only cola? That would be 15%. What's in this cola circle but not in the other 2? What percent drink none? That was the last thing we answered, 20%. And that's as far as we're taking Chapter 5 for Day 1.